and we are going to discuss terrain and surface modeling today. And this is really, like I said, an extension of the stuff that we talked about last week. So we're still talking about digital elevation models. I still have that picture up of the Mississippi digital elevation model there. So we talked about a lot of these: height, slope, aspect, visibility. Today we're going to talk about these: upslope area, flow length. We're going to talk about those, how they're actually implemented in GIS, and how they work, so that you can use these tools for modeling water flow in a raster environment. So just as a quick review, our digital elevation model, a DEM, comes from a variety of sources, and there can be error associated with them. I think we showed the exact same slide last week, so I won't spend a lot of time there. Yeah. Oops. Yeah. Did I downloaded the wrong lecture. Sorry. In fact, the I must have messed up. Really. If you actually manually type the URL, so you probably don't have the lecture. But if you take the URL that would have been for this lecture right here, and you say copy link address, because I uploaded the lecture, I just forgot to change the link. So it'll download the correct lecture 6. Sorry about that. So I'll change the link before the end of the week. All right. Yes, hydrologic surface modeling. Okay. So you need to know about the shape of the Earth for many different fields of study. So this isn't just about water flow. There's a few other things that you can calculate that have to do with the shape of the Earth that are interesting. But if we understand how the Earth is shaped and how water flows on that surface, it can be important for lots of different applications. Some of them are things like development. If we put development here, it's going to change the land cover. That's going to change the way water flows off that area. Okay, that might create additional pooling of water in some areas that we have to mitigate. Those type of changes are going to affect the watersheds. Changes to the slope and changes to the land cover, basically how porous that surface is, are going to affect how water flows off of there. And we're gonna be able to our goal is to be able to model those changes in the GIS so that we can have a prediction. Okay, how is this change in land cover going to change the surface flow of the water, so that we don't have to just build our thing and then figure out, oh, it created a big mess. We can model that. That's the purpose of building a model, is to see how these changes are going to happen, how these changes are going to affect the environment before they're actually put into place. All right, so hydrologic modeling does involve digital elevation models, but you'll see that we're going to use other different data sources because the shape of the Earth isn't the only variable that's important to modeling water flow. All right, so here's a 3D visualization. This was actually using a LiDAR data draped over an area. Here's this representation of the same area with a topographic map draped over the LiDAR data. So you can see contour lines. You should have learned in a previous course, or probably this is something that you just learned growing up, that the lines there on a topographic map represent contours of equal elevation. So, everywhere along one of these contour lines, the elevation is the same. So back when I took a course as an undergraduate in map reading and analysis, we didn't have as many GIS tools. Of course, this was after 1988. We did have GIS tools, but we still learned on paper maps. If we wanted to delineate a watershed, if we wanted to find out what the area was that contributed to that watershed. Okay, we talked about what a watershed was last week. If we wanted to find out where the upslope area of this pour point was, in other words, all the area that flowed, that's outlet point, was that point. Okay, if we wanted to find out that, we would try to trace at an angle that was perpendicular to these contour lines up until we reached a peak, and then follow that contour line perpendicularly along the ridge and manually trace that line. Okay. So watershed boundary can be sketched by starting at the outlet point and following the height of land defining the drainage divides. So you go up at a right angle to the contour lines up to the top, and then trace it. So this is my crude tracing of this watershed boundary. Okay. All right. So that same algorithm can be applied to a computer. Okay. A computer can try to do something similar, and in fact, in a raster environment, it does it in a fairly different way, but it arrives at the same result. Okay, so before we get to how it does that, let's talk about some terminology. So we've got, first of all, a drainage basin. Oh, sorry, I guess I put drainage system up there. A drainage system is the entire system of what we're talking about. We started out talking about a watershed, and the generalized term for watershed is a drainage basin. It's part of the drainage system that drains water to a common outlet. Okay, we call that common outlet right here a pour point. Okay, that's the common outlet. Now, drainage basin is a general term. There's other words: watersheds, basins, catchment, contributing area. Those are all alternative terms for this concept of a drainage basin. All right, a drainage basin can actually have an infinite amount of subbasins. In fact, anywhere you go, there's a watershed defined by that point that you're at. It may be a very small watershed. For example, if I went out, if anybody knows, over here by the oak tree that's on this side of the building, or for you guys that are at the coast, anywhere where you went outside that was kind of in a low-lying area, you probably noticed that water flows to that area, particularly during a rainstorm. And if you could think about the small upslope area that is defined by that location that you're standing at, that you're getting, you're standing in a little stream there, you're in an area that's a small watershed. Okay, and I suppose even if you went up to the very top of a ridge, as long as you took a step off, there would be a watershed. It'd be like a little 1-foot watershed associated with that. But a subbasin is just that. It's a piece of a basin. Okay, and you define a subbasin as an area that's part of a basin. It still has a pour point associated with it. It may not go completely upstream, like in this case. It may be defined by that area that's exclusive to another pour point within the subbasin. So here I've got a pour point. This pour point's watershed boundary is right here. This pour point's watershed boundary would be all of this all of this area plus this additional area. So we might refer to that as a subbasin. Okay. This area is the area that's exclusive to the area in between those two pour points. Okay. All right, we could, in a GIS system, we could figure out what this watershed was and then figure out what this watershed was and do some sort of overlay to find out where the subbasin would be. Okay. Okay, the drainage divide is basically the edge of the basin or subbasin. It's where when you're on one side of it, it's flowing to one pour point, and when you're on the other side of it, it's flowing to a different pour point. Okay. So the boundary between two basins, it's an area of divergent flow. So if you're standing on top of a ridge, that would be a drainage divide. All right, so in a raster GIS model, how do we implement this? Well, one thing we need to do is step back and look at this DEM. Remember that it's a regularly spaced interval of elevation values. So every cell in this digital elevation model represents an elevation, a height above sea level. Okay. Here's a few other representations. Here's a shaded relief representation. We can see, you know, just looking at this shaded relief, this is actually called the hypsometric tinting with the shaded relief, because we've got both the shaded relief portion and then the colors actually represent elevation. We can see just looking at this raster data set that the outlet point is going to be down here. Right? We don't even need to see the lines really. We could have figured that out because that's the lowest point. Okay. We can also see some other interesting things about this particular watershed, and then the upper reaches of the watershed are characterized by lower slopes, and the lower reaches of the watershed have higher slopes, and that will affect modeling water off of that area. So we can do all sorts of things like figure out if a certain rain event happens. You know, if this let's say this area was covered by a half an inch of rain. Okay, how much water are we going to have flowing past this point? Okay, just in total volume. We can also measure it as a hydrograph. In other words, we can measure how much water is going to be flowing to this particular location over time. So, and that has to do with the shape of the watershed. Here we have some pretty low slopes, so it may take a long time for this water to get down to that point. Here we have some pretty higher slopes, so we might initially see a large amount of runoff, and then have a delay before this runoff reached the end of the watershed. Okay. So those are the types of things that we would want to model: the total amount of runoff, and the amount of runoff at different time periods. Okay, so how is it actually implemented in a GIS system? It's a concept that's kind of similar to what we talked about in when we did slope, where we discussed what is slope. Slope is the direction of the change. I mean, sorry, the degree of the change. Aspect is the direction of the change. Is the degree of change that occurs through that window of 9 cells. Well, the first algorithm, the algorithm that's discussed in the paper that I had you read, or that you'll probably read over the next few days, is that it uses the local drain direction. Okay, instead of figuring out the change through all 9 cells, it's only concerned with which direction had the steepest drop or the biggest drop. Okay. So the slope from the target cell of each neighborhood is calculated. So instead of calculating the slope over all 9 cells and reporting that as the slope of this cell, what we're doing is saying, okay, from here, from this target cell, what is the slope to this cell? What is the slope to this cell? What is the slope to this cell? And so on. So in other words, the slope to this, let's go to let's go, well, yeah, let's go to 9. Okay, what's the slope in this direction? Well, the slope is the rise over the run. So we could calculate that as what's the rise there? It'd be -1, right? We're going down 1 unit because these represent elevation. So let's say they represent feet. So we went down 1 foot in this direction. From 10 to 9, we go down 1 foot. Now, what's the run in this case? It's a little bit tricky. I should have maybe started off with 1. Okay. It's the cell size related to the cell size, but in this case, since it's a diagonal, the computer actually accounts for that, or the algorithm that's implemented in the computer accounts for that. So the slope is the cell size times the square root of 2 is what it works out to be, and that's just the Pythagorean theorem. So a squared plus b squared equals c squared. This is the hypotenuse of a triangle that would have the cell size on this side, the cell size on that side. So this side would be the cell size times the square root of 2. Okay, so it would be 1 divided by cell size times the square root of 2. Okay, so the next thing that it does after it calculates all those numbers, so it comes up with a number for those. So I just have like a 1 divided by the square root of 2. And in fact, since we're using the cell size, we could, on all of these, we could probably just throw it out. So these could all boil down into a number. Okay, and what it does is it looks for the greatest slope, and it's coded into the target cell. Okay, so in this case, we've got our target cell, and I've gone ahead and calculated the slope in degrees to each of these cells. It's got 8, 17, 11, 6, 0. Those are all positive slopes. And so if we have a positive slope, that means that it's uphill, okay? And the water's going downhill. And so there are several algorithms that are used for calculating that local drainage direction. And the one that's talked about in the paper there is probably the most widely adopted, widely used. It's implemented in ArcGIS. It's called the D8 algorithm. So in that case, D stands for deterministic. In other words, it'll always produce the same result. Okay. So here in this case, we've got the target cell, got the output units, and what ArcGIS does is in the raster GIS system, it assigns a value from 1 to 255 based on the direction that the water would flow out of a particular cell. So, it actually looks like this. So it looked like 4 in this case. The value, if it went right to the west, would be 1, 2, 4, 8, 16, 32, 64, and 128. So if it flowed in this direction, in other words, the northeast, you'd get a value of 128. If it flowed directly to the south, it'd get a value of 4, and so on, like that. All right. So in this case, it would get a value of 4 because it was flowing directly to the south. Okay. The slope there was -11 degrees. Now, it might not have looked like that because these were both 8. But remember that the slope was going to be greater going directly due south because that's a less of a run than this direction. Okay, we did talk about this briefly in the last course, but why would we use this schematic? Well, this provides a unique number for each direction: 1, 2, 4, 8, 16, 32. So we've got a unique number in each direction, and we can add any of these numbers together to get a unique combination. And that's what we do if we have 2 drops in 2 directions that are the same. Okay. In other words, if we have If we have what this example here that I cut and pasted from the article there is, what if the drop to 1, 2, and 4 are all the same? In other words, the drop in this direction, the drop in that direction, and the drop in that direction are all identical. Well, ArcGIS will temporarily encode that as a 7. In other words, it will encode that value as a 7, meaning that it's going to flow in this direction. And a 7 is a unique number. It's not any of these other numbers. Likewise, a 1 and a 3. Sorry, a 1 and a 2 would give you a 3. That's unique. A 1 and a 4 would give you a 5. That's also a unique number. So every possible combination of these cells is a unique number. It's a number. It's going to be a number between 1 and 255, and it will tell you exclusively that it flows in a single direction, or it will tell you that it flows that it could be one of 2 possible, or 3 possible, or 4 possible choices. Okay. All right. So once this process is done, you get a map that looks like this. This is called the flow direction digital elevate. This is called the flow direction data set. Flow direction data set showing you which direction each of the cells is flowing in. Now, different GIS systems will actually implement. So in the book here, not the book, the paper here, it says, and then resolved iteratively. And so different GIS systems will resolve that conflict of it flowing in 2 or 3 different directions and produce a map that looks like this. So every cell has a direction that it's flowing. The next step after you pre-process, after you create your digital elevation model, is typically to take it right into flow direction. But if you do that, there's going to be some issues. First, digital elevation models have some problems with them, and one of the problems is that even in real life, there are situations where digital elevation models have depressions, and modeling water flow in this manner is a problem, because water will flow into a depression and then it will never flow out. In order to solve this issue, in order to overcome this issue, what we do is model what would occur if we had a depression that was filled up entirely. At that point, the water would flow into that depression and then flow out somewhere else. So the first step is often to pre-fill our digital elevation models. Pre-fill them. We call those areas sinks. Okay, those depressions, we call those sinks. And ArcGIS will, or in fact any other raster system will allow you to fill those sinks. Okay, they have to be removed. The way that they get removed is to fill them up. So assuming that they're all full of water is what the process does here. So here's an example of a sink using hydrologic modeling. This sink right here, none of these cells would flow out anywhere because this is a value of 98. Okay, so this cell would flow to this cell, which would then flow to this cell, and same with this one. This one would flow probably actually, yeah, in the same direction. This one would flow to here, then to here, then to here. So they would all flow, but at this point, this cell wouldn't flow anywhere. There's no greatest drop that's negative. All the drops are positive. I shouldn't say they're drops. All the neighboring cells are positive. So the only way that we can model flow out of this particular sink was to fill this depression up so that it became as high as this cell. So then the water would flow out through this cell, and we would have a valid digital elevation model for modeling flow over the water. So here is a profile view of a sink. Here's a profile view of a peak. We're going to raise up sinks. We don't actually lower peaks. We raise up sinks in the modeling technique. Now, if it is an error, like if we know, for example, that this happens all the time in digital elevation data. What if this is actually a freeway overpass? And in real life, a freeway overpass does have the ability for water to flow underneath it, right? Okay, we don't have to fill up the upstream area for the water to flow over the top of the freeway overpass. That doesn't make any sense. Okay, and so sometimes, in fact, this is good. This is good to remember. Sometimes companies that produce digital elevation models will, if asked, produce a hydrologic a hydrologically valid digital elevation model. And what that means is that they'll remove any feature that allows water to flow underneath it, okay, like freeway overpasses, things like that. So if like let's say you're purchasing a DEM or you're downloading a DEM, you may want to know if it's what we call a bare earth DEM. Okay, that means that all the trees and vegetation have been removed, or is it a hydrologically valid DEM where they've also, in addition to that, removed any features that would be normally considered ground features that allow water to flow underneath them. Sometimes this even involves etching out, a culvert, right? That would normally allow water to flow through it. Okay, so these kinds of things, if they are in fact preventing water flow, and they shouldn't, have to be removed manually. These type of things can be removed by the fill sinks algorithm. Okay. All right, so that's kind of what I was talking about. Drainage enforcement. Using existing hydrographic features to remove these errors is essential to produce accurate watershed basins. Okay. Sinks, usually small, they cause drainage basins to be incorrectly delineated. You do have to pay particular attention, though. In some areas, water, there are significant underground channels. There's karst topography where we've got lots of limestone cavities in areas, and the water actually flows in there, flows underground. This happens a lot, like in Florida and other islands in the Caribbean, where they're karst. In other words, they have big depressions, and the water drains through those and drains underground to another location. And this particular technique wouldn't be as good at modeling water in those cases. All right, the operation in ArcGIS, the implementation is called fill sinks. All right, it is an iterative process because when you fill one sink, it might actually inadvertently create another. So ArcGIS runs through and keeps filling the sinks slightly until it's able to create a flow direction grid that's valid. Okay. This is from the I keep calling it the book, but from the article that I had you read. So this follows you through the basic steps. This is what we're going to implement in the lab. So the first step is to fill the sinks. Second step is to compute flow directions, and then from there you're going to do a few other things that we could talk about. You can build watersheds. You can, using pour points. You can actually start to build paths. Okay. The way that you start to build the path of water flow, in other words, you can start modeling where stream channels should exist, is called flow accumulation. Okay. Flow accumulation is modeling the number of cells that flow to a particular point, okay? And we know that if more cells are flowing to a particular point, more water is accumulating at that point, and we might model that as a stream, okay? So we can trace backward up the flow direction grid. We can find the number of cells that flow into a particular study area. So it's the accumulated flow, the number of cells that are flowing into each downslope cell. So that's the key thing here. Okay, a flow accumulation grid, what do the numbers represent? The numbers represent the number of cells that are flowing into that cell. So if it has a value of 10, that means there are 10 other cells that flow, the flow direction leads to that cell. Okay, if it's 1,000 other cells. So if we were to use that cell as a pour point, it would show us which 1,000 cells flow into that cell. Okay. So that's kind of the connection between flow direction, flow accumulation, and a watershed. So we know what the number is, we know how many cells. If we ask it to delineate that watershed, it'll show us which of those number of cells it does. So in fact, you should be able to, if the number is 1,000, you should, after you delineate the watershed for that cell, you should have 1,000 cells in your watershed. All right. Okay. Yes. So after you do this, cells that have high accumulation are areas of concentrated flow, and those can be used to identify stream channels. In different areas, the threshold of what a stream channel is will be different. In some areas, the soils may be more porous. There may be more rainfall to begin with, and it may take less accumulated cells to form a stream channel. In some areas that are hot, dry with porous soils, there may be a channel there, but the stream would be intermittent. So sometimes it takes some trial and error to decide whether or not a stream channel really exists at that point. So this is a flow accumulation surface. Got our flow accumulation surface there. And you can see that there are actually several, for this particular watershed, there's several areas. Like this one's flowing here, this one's flowing out to this area, and these are all flowing out to this area. So there are minimum three different watersheds with some drainage divides occurring somewhere around these areas. Flow length surface is the length from the outlet back up. Okay, so the outlet is close to zero or zero, and then outlet, the flow length for each cell is the distance along the flow path back to here. So we can see if you're up here, you got a very high flow length because you're traveling, down through this area along the flow direction grid. Similarly, up here, traveling down along this grid. Okay. So this grid, every cell represents the length to travel back to the outlet point. That's flow length. So this is another variable that can be used to model how much water is going to reach a certain point at a certain time. Okay. All right, so far everything that we've talked about, and we did discuss that. I realize that up to this point there's a little bit of a review here. Okay, we discussed it in the last course. We got our digital elevation model. We could calculate flow direction first. Lots of times people just go ahead and calculate. Computers are fast nowadays. People calculate sinks or fill the sinks first. Fill the sinks, then do flow direction. It's kind of an iterative process. We've got, from our flow direction, we could calculate flow accumulation, flow length, and then we could calculate things like watersheds, basins, and things like that. There are a few other tools that we'll go over in the lab. One of them is called Snap Pour Point. Snap Pour Point, what it does is sometimes when you're delineating a watershed, let's like this real quick. Sometimes when you're delineating a watershed, let's go back to our very first example here. Sometimes when I'm delineating a watershed and I say, I want the pour point for this point right here, and I click on it, I accidentally, sometimes you can be, if you're off by one cell, especially down towards the end of a watershed, if you're off by one cell, you could pick a cell that has a very small watershed that's just right next to the river, like just right here. That there might be some areas that only flow into the river there. It's particularly true on a really big, like if I had a DEM of the entire United States and I picked a water, I was trying to find, like, let's say the Pascagoula watershed. Okay, that comes out to a small area by the ocean. I picked a cell, and I might get some neighboring watershed that's it's not very large. And so what Snap Pour Point does, it's a tool for delineating watersheds. It sets a threshold and it tries to find the maximum value within that threshold, and it makes that the pour point. The maximum flow accumulation value within a certain threshold, and it makes that the pour point. Okay. All right. Now let's discuss a few alternatives. This is the most widely used alternative. This one here, the 8-direction pour point model, where you begin with an elevation grid. The flow is modeled as the direction of the steepest descent. Okay, so we start with our elevation. We get a flow direction grid, which looks like this. Then, after that, we could actually directly take the flow direction grid and create what we call a network. A network is just a set of lines that follow the flow direction grid. And we could thin out those lines based on the number of upstream cells. So we could say, okay, well, there's only one, so we'll just get rid of this line, this line. We're going to thin out the lines. We're going to set some sort of threshold. It has to be greater than 20 to be a stream. So we're going to model where the streams are. So that's the flow accumulation. So our streams, actually I said less than 7 here. So 7 and above get counted as a stream, those that are in blue. Okay. 7 and above, or greater than 6 is another way to say 7 and above. All right. So here's flow accumulation on an old GIS system. Okay. I think I covered most of this. I already mentioned culverts, bridges, engaging stations, watersheds can be created for a spot. We're all going to practice this in the lab. I was going to show it last week, but I just never got around to showing it in the lab last week. But you can, when you create an ArcGIS toolbox, you can specify that you want that toolbox to be able to interactively choose a point. So like for last week, or no, 2 weeks ago. 2 weeks ago we did the, anyway, in any case, remember when we did the cost surface modeling. So instead of you feeding it up 2 sets of points for the source and the destination, you could alternatively say, user, click on a point that represents where you want the destination to be, and then use the same source. And then they could be clicking on these points and always finding the direction back to a particular point. We can do the same thing with hydrologic flow. So we could interactively choose a point to be the pour point. You can input a pour point as a entire theme or a layer. Theme is an old way to say layer, sorry. Or they can be created by selecting a point on the screen. So you can actually, as an alternative to selecting a pour point, you can actually have ArcGIS kind of separate out the area. This is similar to what has been done. Anybody know what the hydrologic, what we talked about this in the last course, but the USGS has a set of hydrologic units, or HUCs, and this is similar to what they've done there. Is they basically said, okay, just separate these out into watersheds based on kind of a minimum size. They have to be a certain size. They're not strictly watersheds. They're sub-basins in a particular area. So this would be how it's implemented. We choose a pour point, we get a contributing area. Or instead of defining a pour point, we could say, okay, this is our study area. Divide this up into a minimum catchment area of 5,000 cells. And so what it does is creates basins and subbasins. This is obviously a subbasin because the water flows out to this point, but this subbasin and this subbasin both flow into that basin. Okay. So you can set it up to have a minimum number of cells. This is 5,000 cells. This is 10,000 cells, and it will create larger watersheds. And you could create a nested set of watersheds inside of other watersheds. For example, if you wanted to divide up an area for study. And like I said, there's a national data set called the HUC data set that's done exactly this. The HUC 8s, we just discussed this in the last course, but there's HUC 8s, there's HUC 10s, there's HUC 12s, and as you get, actually the higher number means it's a smaller and smaller watershed. So you can download those, and it's good to utilize those in studies that will be used with other national data. All right. Now, what can you do with this sort of information to actually model water flow? Okay. Well, here's an example of something that you could do to implement. You can implement this in a GIS system. Okay. You could take each of these terms here and model them in a raster and figure out what the S term here. This is a surplus water per cell. So we're trying to figure out how much water is going to leave every cell, okay, based on the input precipitation, that's P, the infiltration, I, okay, there's a constant term here, and then the evaporation, okay. So we can probably hold a lot of these constants. So the main inputs here are going to be the input precipitation and the infiltration. Okay, so for every cell, how much input precipitation is there going to be? How much infiltration is there going to be? The infiltration, what might be some sources of GIS data that we could use to model infiltration? Soils, exactly. Another land cover type thing, like we could have impervious surfaces that, like asphalt or concrete, and those would have very little infiltration. All right, precipitation. Okay, we could get that data from some weather service or from NOAA. We get some input precipitation data. We could actually be modeling that. We could not necessarily. We're not necessarily modeling a past event, but maybe a future event, saying, okay, there's going to be this much precipitation over this area. And so we can add these values together, and I got some of my slides cut off. We could add those values together and model the. So what would happen is, if we had infiltration, that might be a submodel by itself, right? So we've got infiltration, and that could be taken from soils and from land cover. And we could come up with a mathematical expression that would yield what infiltration was. And the amount of infiltration that occurred at a certain location would then be used in combination with the input precipitation, how much water actually precipitated at that cell. And so the infiltration would just be multiplied by that precipitation value. So if 30% infiltration occurs at that particular cell value, and 1 inch of water fell on that particular area, then we would have 0.7 inches of water left over. We could figure out the volume of water because if 1 inch over the cell size, we could figure out the volume of that water. And then we would know how much water was going to leave that cell. Does that make sense? So we've got a number that represents how much is going to stay in that cell as a percentage, and we multiply how much actually came in, and we get how much is going to leave the cell. Okay. And then what we can do at that point is to run the flow direction, flow accumulation data sets, and we get a value that represents the amount of water that is traveling out of every cell, right? So we get a number that represents how much water is traveling out of every cell. What would the next step be? Let's think about what we have. We have flow direction, and that doesn't really matter except for we can use that to calculate flow accumulation. How could we use flow accumulation along with that number that represents how much is flowing out to get a number that represents how much we've got total? Sorry about my slides being missing. Here, I'll show you what I mean here. Okay, so let's look here. Let's just do this in all right, so let's say I've already gone through the process of creating a watershed, okay? And that watershed has a value. That watershed is just going to be a little 3x3 watershed, okay? And it's going to flow out here, okay? 5, 6. I've got numbers here that represent. These numbers are going to represent numbers. This is how much water is flowing out of each of these cells, okay, based on the infiltration number. And so I already took infiltration and I multiplied it by the precipitation to get this number, how much water is going to flow out of these cells. And they're all going to flow out to this area here, okay? Going to flow out to there. I've already calculated. I've already done flow direction. I've calculated that. Now, if I said that this is the entirety of the watershed, what would the flow accumulation value of this cell be? If all these cells are going to flow into this cell right here, these cells right here aren't flow into other cells, but this cell is going to get all the flow from these areas. So what's the flow accumulation of that cell going to be? What is flow accumulation? Total number of cells. Right, the total number of cells that flow into that cell. So what's that number going to be? Yeah, 9. I actually don't. I'd have to go in and see whether or not it considers the cell itself. It's going to be 9 or 10, but it doesn't really matter. And so we're going to get a value of 9 here, but that's the flow accumulation value, not this. So these numbers actually represent the amount of water flowing out. This represents flow accumulation. Okay, so we've got a 9. Okay, and so here we've got all these values, and we know that it flows into that cell. How much total will flow into this cell? How much total is going to flow in? How would we calculate that? Yes, we could sum up all these numbers, right? Okay, now if we had built this inside of a GIS system and we built a watershed, that watershed would all be coded the same value. What operation could we use to figure out how much water was going to flow off of there that we discussed earlier? what if we were to set this up? So we've got first of all, we fill our sinks, we get there. Finally, at this point, we would click on this one and create a pour point, and then that pour point would delineate something that looked like this. You know, it would delineate a watershed that it would delineate a watershed around that area. So we've got our watershed that didn't draw very well, but we've got our watershed that includes all 9 of these cells. Okay, so if we wanted to find out how much water was flowing off of those cells, we would implement that using zonal statistics. Does that make sense? We find the zonal sum of those cells and figure out how much water would flow off during that rain event. So that would just be like this, the sum of all this stuff. But that's how we would do it, is to use zonal statistics. So we come up with a number there.
Would you need to know like the precipitation at that moment?
Yeah. So exactly. That's what I was trying to say before. Let's say we had so this is the exact same watershed. So we have our infiltration values here.
Infiltration is like just incoming water.
It's the amount of incoming water that the in this case I'm doing as a percentage. That may or may not be an accurate way to do it, but so 30% of the incoming water will stay in the cell. 33% or 30%, 40%. So these are the same exact cells. Okay, and then what I could do here is if I actually had a model of, if I said 1 inch went everywhere, it may be that's the way I wanted to model it. I got 1 inch of rainflow over the entire precipitation. It may be that I actually got like, you know, 6 inches in some places and 5 inches in others. I mean, that type of data does exist. Okay, so I've got 6 inches in some parts of my watershed and 5 in others, and then this one would just be equal to this times this. Okay, that's how much water is going to flow out of that cell, and I could fill this through the rest of the watershed. So now I've got these values tell me how much is coming out. Now, in reality, though, this is 8.2, but the problem is there that I forgot that this 1 inch is 1 inch over the cell size. Okay, so now here at the end, I have to multiply this by the cell size times the number of cells. So that's why I had that's why I was holding that 9 value out. So if I want to get, let's say the cell size is 10 meters by 10 meters. Then actually let's keep it in inches. Otherwise we're going to get confused. So the cell size is 1,000 inches by 1,000 inches. Okay. So what I could do is I know that if there's 1 inch of rain over a certain area, how much volume of water is that? Well, it's 1 inch times 1,000 times 1,000, which would be, let's just say 100 inches because it'll be easier. So that would be 10,000 inches. Okay. So if I say 10,000 inches times 9 cells times the amount of, now this is still the same units, inches, I get a number that's 73,800 cubic inches. Okay, and I could convert that back into feet, which would probably be a nicer number. So I could say the total amount of water that is going to pass by this pour point is going to be 73,800 cubic inches of water. Okay. Now I could model this temporally if I had that information now, where that I would have to find out how much is coming out in different time steps. Okay, I could calculate, what I could do there is calculate the flow length back up to these points and figure out how long it would take each of those to arrive back at that at the outlet point. But I do know that this is the total. Okay, that's the first step. So what I'm trying to say there is, if I did want to create a hydrograph of this area, so, oops. So this might represent time, and this would be flow. At the pour point, okay? So hydrographs are going to look like this. Okay. So when the rain event happens, they're going to ramp up, and then have more flow. So what I'm saying is the number that we've calculated so far represents the total. We haven't broken this out temporally yet, but we've calculated the total, the amount under this curve. Different watersheds will have different characteristics. Like some watersheds, you might get the exact same amount of runoff, but it might look more like, more like this, and slow. Like if it has a big flat upslope area, it may continue for a long time. And this is where, like if you watch the news and we have a big rain event, this type of modeling is what says, okay, well, it's going to crest at this particular time, or we think it's going to crest at this particular time, because we can see that. Because what you could do is model the flow, and then what time it crests, okay? Because that would be this time. The time to crest would be that time right there. Okay. That would mean the maximum flow for that particular rain event. Okay. If you had several rain events over a time period, you could plot both of them. Okay, you could plot both of them on a piece of paper, offset them, and then add them up cumulatively, and you would see how they would. You could then also model again what time that they would crest using that particular technique. All right. So what we've calculated there is the total area. And when later in the course we're going to talk about temporal modeling, we could take this a step further. But you could see right now how you would do that with flow length. So each of these values would have a flow length associated with it, and the flow length could be modeled as time. Okay, and so you could. What operator would you use to get that? You could separate things out by in different time periods and figure out how much was going to come at different times. There's a few different ways to approach that. Okay, but this is the total, calculating it as the size of the cell. It has to be in the same units as the precipitation, times the number of cells, times the total runoff. Now it's multiplication, so we could have done the multiplication up here. We could have taken these numbers or these numbers actually and multiplied them all by. We could have multiplied them all by the cell size. Okay. Because it's multiplication, you could throw it in anywhere. We're multiplying, so neither one of them are exclusively correct. Okay, throw the multiplication problem in. So for the lab, what we're going to do is actually we're going to do something very similar to what I've shown you here. We're going to calculate it. We're going to calculate it manually first for a small area, just so that you'll get a chance to do what I've shown you here, and then. We're going to implement it as a GIS model. So your GIS model will follow the what you've probably done, if you took the last course, you've done it before. You'll create a watershed, and then after you create a watershed, you're going to use the parameters that I gave you, because the parameters will be different in every watershed that you're at. Okay, you have different infiltration values, different runoff values, and so you'll take those values, you'll put them in your model, and the last step in your model will be to use zonal statistics and a formula like this to figure out what the total runoff is for that particular watershed. So we'll make a toolbox that does that. That'll be the lab. Okay. All right. So if we look back here, we do have a little bit of time. I'll do this for a few seconds. If we look back at the lectures, I have, this is probably not valid. But if you go to other materials, yeah, that's not valid, because the course was significantly redesigned. So now we're only talking about raster in this course. So I'll update these two things, because this is from an old course. So what I'll do is update the midterm study guide. I started writing the exam itself already, but I always like to have the exam written first before I create the study guide. So I'll have that all ready by Thursday and post that here. But if you go back and look at the lectures here, you'll see the content. And really, what's going to be on the exam is stuff that you can find in the lecture notes and what we talked about, and with some of the concepts that are harder, refer to the readings. What you should be able to know is, for each of the different types of modeling techniques that we went over hydrologic modeling, we went over terrain modeling, cost distance modeling. One of the keys is going to be knowing what the cell values represent in a particular operation. So when I do, cost distance modeling or surface modeling like we talked about today. So in the flow accumulation grid, what do those cells represent? The number of cells that flow into that cell. Okay, in a cost distance model, you need to know that every cell represents the cost to get back to the source for that particular cell. Okay, so that's going to be probably, I don't know, the majority of the test, not all of it, but a majority of the tests are going to be those sorts of things. And we'll discuss this a little bit more, but that's the kind of thing that you should study. You need to know a few of the map algebra functions we talked about, particularly the conditional operators, and to be able to manually recognize what the output would be. So if I have a conditional operator on a single cell, you should know what the result would be for that particular cell. All right. Like I said, we'll talk about that a little bit more. It's not multiple choice. It's not exclusively multiple choice exam, but there will be some multiple choice questions. But it's mostly short answer, give the answer type of the test. Anybody have any questions at this point about that? All right. Great. Well, I'll go ahead and end about 10 minutes early here today then. If nobody has any questions, and we'll meet again on Thursday, and I'll go over the test exam. I'll go over the exam then. All right, I'm going to go ahead and shut off the broadcast.